Professor Edwin van der Weide of the Department of Mechanical Engineering at the University of Twente, a fellow Dutch here. Hello, Edwin, the floor is yours.
I'm muted. Yeah, no, I'm not muted anymore. Yeah, thank you very much, Pedro, for the introduction. Welcome, everybody. Good morning, afternoon, evening, depending on the time zone where you're in. I would like in this presentation to give an overview of the work that we have been doing and are doing on the high order discontinuous Geluk in finite element discretization in SU2. You heard a talk yesterday also about high order schemes. That was on Reno schemes. That's a different way of getting high order accuracy, but we are here focusing on the discontinuous Geluk in approach. So, okay, that the arrows are not working. Could you do next one? Yeah, thank you. So to give an outline of the talk, first of all, the motivation. Why do we need a high order scheme, or do we need high order schemes? At the moment, there is already a discontinuous Geluk solver available SU2, and I'll discuss what it can do and also what areas of improvement there are for the current implementation. And it turns out that these areas of improvement are such that we basically had to do quite a bit of a new implementation. I'll discuss that, and that's currently available in the branch feature home new. Those new data structures were based on the results of a couple of test codes, and I'm gonna show some results of those test codes. They're mainly the VCP 3D and the Incompressible plane and lattice 2D code. If I have time, which is probably a bit difficult, but we'll see. Let's have another time. We'll see if it's time for some additional topics. That will be brief anyways. And I hope to conclude with some future work and plans what we still have in this respect. Next, please. Okay, the first question you can ask yourself, why do we need high order schemes? Because, well, during these 3 days of the SU2 conference and also for other years, you've seen extremely, well, complicated application with second order finite volume schemes. It's used for many applications, and finite volume scheme, second order finite volume scheme has been the workhorse for, well, at least 35 years, I think, in CFD, and it probably will be for another, well, in the foreseeable future at least. So you can ask yourself, why is it needed? Well, why do you put your effort on high order schemes? Could you go next, please? There still are a couple of applications for which second order schemes, well, second order accuracy may not be entirely sufficient. I've listed here a couple, and the first one where you have wakes and vortex flows that have to be transported over long distances. Sufficient may not be the right word here to use. It may actually more be efficient. May be better, because you can always obtain a good solution if you go use very, very fine grids. Huh? But if you have reasonable handleable grids, it is well known that second order finite volume schemes have a tendency to diffuse vortices and wakes rather quickly. And if you're interested in the transport of these wakes, you either need very fine grids or maybe you need high order accuracy. Same is true when you do noise prediction. And when I started this work, I also thought, well, for LES, DNS, it's a no-brainer. We can use this high order schemes as well. But there's a little bit of, I put a question mark there, because what you're going to see tomorrow in the talk of Paul and Eduardo, some very complicated applications using LES with the second order finite volume scheme. We can do it with the high order DG schemes as well. But the benefits are, well, at the moment, not that obvious. And the very simple reason is that the high order schemes, well, they perform as they should, and they give you a high order accuracy, but only in the asymptotic range. And by definition, LES is never in the asymptotic range. So still, people are still debating whether it is better or not, whether it's better to use high order schemes there or not. But as you can see in this picture on the bottom left, we can do it. But you can also do this with second order finite volume, and the question remains whether which one is still most efficient one. So, but in order to do so, well, the proof is in eating the pudding, huh? So you have to do it, and then you can do the comparison. Could you go next, please? Very short way of the basic principles of a discontinuous Galerkin discretization. What you have here, yeah, you can see my mouse. Yeah, you can see my mouse. What you do typically to obtain high order accuracy in a finite element setting, whether it is in a continuous setting or in a discontinuous setting, is that you do a polynomial expression here inside an element. Yeah, so typically what you see here is a certain variable, and that you can vary up to an arbitrary polynomial degree. So this is in contrast to what you saw in the talk yesterday when you do the Wiener schemes in the finite volume framework, where you extend your stencil in order to obtain higher order accuracy. You typically do not do that in a finite element framework. What you there do is you increase the polynomial expansion of your problem. Yeah. So if you have a system of PDEs, what you see here, typically you end up with a weak formulation. I'm not going to discuss all the details here, but you typically integrate it over the control volume, apply Gauss theorem, etc. The same what you do for finite volume, and then you end up with the so-called weak formulation that you solve in your finite element method. And here this phi's over here, those are the test function. And if you take phi equals 1, then you end up with a finite volume formulation, because in the discontinuous Galerkin framework, you take the integrals over the control volumes, and that's a contrast to the continuous framework where you take the integrals over the entire volume. Yeah. So if you take phi equals 1, as I said, you end up with a finite volume expression, and basically a discontinuous Galerkin can be seen as a kind of a hybrid between a finite volume and a finite element discretization. Yeah. But anyways, it boils down, finite elements discretization boils down to computing integrals. Yeah, and here you see the integral over the volume, and here the integral over the surface elements. And when you have high order polynomial representation of your solution inside an element, that means that these integrals have to be also computed with quite high accuracy. For example, if you we have a nonlinear problem, Euler equations are nonlinear, and so are the Navier-Stokes equations. If you take, for example, fifth p equals 5, so a fifth order polynomial, and in order to avoid aliasing, you have to compute these integrals up to exactly up to a degree of 15 or something like that, 12 to 15 on these elements, and you use Gaussian integration rules for that, and you can imagine those become very, very costly. So the DG discretization is computationally very intensive and costly, but the good thing of it is that it runs very efficiently on modern hardware. You could go next, please. What's also needed, because we have this high order polynomial representation of the solution inside an element now, we need curved elements in order to represent the geometry correctly. In order to do so, we have some in-house capabilities to generate high order grids. Open source for software can do it, GMS in particular. And yesterday you saw the talk of Travis from Pointwise, and they also give now good support for creating curved elements for even very complicated geometries, and so do other vendors. But I will not pay attention to this, but you have to keep in mind that you have to do this. All right, go to what is currently available in SU2. Well, this is a little bit of a detail on the nodal formulation. I will not go in detail of that. But what you do have in the finite volume solver is both 2D and 3D, and that's also present in the DG solver. All standard elements can be handled, so triangles, quadrilaterals, tetrahedra, pyramids, prisms, and hexahedra. Curved elements of an arbitrary order. And what you also saw yesterday in Travis's talk is that it is possible to have different polynomial degrees inside the elements. We can handle that as well. We use certain discretization for the viscous fluxes, and at the moment all time integration schemes are explicit. Either it is of the Runge-Kutta type, or it's local time accurate local stepping via so-called aider discontinuous Galerkin. And we have also support for LES models and shock capturing. Could you go next? And we've run this one, so it is working correctly. This is the actually simulation done by J1 from Stanford a couple of years ago, and here you can clearly see that this is an implicit LES simulation of the SD7003 wings of a relatively low Reynolds number, and you can clearly see the transition from laminar to turbulence over here. So it is working. Could you go next, please? But there are areas of improvement, and the main reason for that is that the original design, if you do the amount of flop counts, you clearly see that the jam calls, so the matrix multiplications, are by far the most flops in a DG discretization. So what we thought we had in mind, so we have to optimize the jam calls no matter what. So that was the basic design of our data structures, and we do get that. We get 60% peak performance on the Xeon, but in order to get that, the code is rather complicated and basically not very well readable. And in order to obtain that performance, quite a bit of copying of data is required for that. And now it turns out that yes, the gem calls are running very efficiently, but the other parts are running not so efficient. And it turns out that in terms of wall clock time, actually the jam calls are not the bottleneck anymore, but the other parts. And the other parts, unfortunately, by the choice of these data structures, cannot be vectorized efficiently. Yeah, that's on the, say, the data structure part. And the other side is that we use conservative variables for the polynomial expansion, and it turns out that that may lead some instabilities for high Reynolds number. And this so-called nodal form what we had chosen, that's apparently not so well suited for the incompressible version, as we're also interested in an incompressible version of this discretization. Could you go next, please? So that's why we saw this about a year ago, and we wrote a couple of test codes, and we saw significant improvements with different data structures. And that's the reason why we bite the bullet about a year ago and decided, all right, we're going to start redo this thing. And that's now in the branch feature home new. And I'm not going to discuss everything. I'm going to discuss the important ones here. And so the new data structures, they are suitable for vectorization. That's basically built all on what Pedro has been doing on the vectorization part, on the performance improvement. He will discuss this later today. So we leverage all of his work, what he has been doing, both for vectorization, but also for the hybrid OpenMP and MPI parallelization. So, well, you just, as I said, we just leverage that, and this is all the work done by Pedro, and you can just use it. So that's a good thing. We use a different form of the polynomial expansion, which can be used for both the compressible and the incompressible equations. For the compressible equations, we are quite far already with the implementations, but for the incompressible equation, we just have the preprocessing part. And in order to avoid a lot of copying, now everything is handled via standard elements. You have to keep in mind that if you use a high order discretization DG, then the relative orientation of the elements matter. And if you you work it out in 3D, you can easily see that you have roughly 1,000 possibilities for this orientation. So that's a little bit many. Well, if you do it smartly, you can get away with the square root of that number. But it turns out that we had to do 30 or 40 different situations, and we all coded them by handling via the standard elements. We used optimized tensor product formulations for hexes and quads because that's more efficient. And for the other elements, we used, well, if you can use the MKL, you have optimized jitted kernels, and if you cannot use the MKL, you better use OpenBLAS or something for good performance. Yeah, and unfortunately, the output routines are not there yet, so we still have to work on that. Could you go next, please? So discuss some results. So this is the result of one of the test codes. This is the incompressible. This is the compressible test code VCP3D. It stands for viscous channel periodic 3D. Although we have we extended it such that it's also able to handle relatively simple geometry, such as this airfoil geometry. This is again this SD7003 test case. Implicit LES, Reynolds number 60,000 alpha. 8 degrees, so angle of attack, and we used hexahedral elements with the polynomial degree of 5. And here you see the movie of the Mach number, and you clearly see again here the transition from laminar to turbulent going down. Okay, could you go next, please? So what we did here is we take an average, and this is a plot of the average solution. What you also see here is the computational grid, and what you have to keep in mind, because this is p equals 5. That a computational cell is composed out of 6 by 6 points here, and inside there you have this polynomial variation to give you an idea of the type of the fineness of the grid what we are using here. Here you clearly see in the streamlines the separation part, and if you plot the skin friction, we actually get this solution. So here is the upper side. Here you get the separation, and here you get the laminar to turbulent transition via the laminar separation bubble, and you end up here with a turbulent flow. We did a comparison. This is typical. This was a test case of one of the high order workshops, and we did a comparison with other solvers, and this turns out to be quite a good comparison. Yeah, so we were pretty happy with that formulation. Yeah, could you go next, please? On the other side, we also been when we had our meeting in Verona, we had I had quite a bit of a discussion with Alexander Linke from the Weierstrass Institute, Mathematical Institute in Berlin, and also Nico was involved about can we use SU2 also for the DG discretization, also for incompressible flows. And well, we started discussing, and it's actually quite funny if you if you have a discussion between an engineer and a mathematician, but at the end we understood each other. And the result of this is that we started with a test code just to check what we can do. And here, this extremely exciting movie you see here on the left is an exact solution of the incompressible Navier-Stokes equations. Yeah, and here the right you see the actual formulation of it. So it's very spatially with a sine function, and in time it's e power. Yeah, so this is here you see the pressure, and you also have solutions for the velocities, although with a different frequency. Could you go next, please? In order to do so, because the incompressible Navier-Stokes equations, as you all know, they are kind of funny equations because the continuity equation doesn't have a time derivative. And in order to do so, you have to reduce the polynomial order of the pressure to avoid odd-even decoupling, the same what you have in the finite volume context. And if you use staggered grids, you can get away with it, but you have to do some tricky things. Okay. In order to do so, I'll see it, Piero. I'm almost done. In order to do so, we used a 4-stage third-order scheme because that has a stability domain. The explicit part contains the imaginary axis, which is needed for the skew symmetric, so dissipation-free discretization of the advection terms. Yeah, and although it's third order in time, it turns out to be that's only second order in time for the pressure, and that is basically related again to this problem of the incompressible Navier-Stokes equations. That the pressure is a kind of funny variable there. Well, can you go next, please? Well, let's skip that one. Let's skip the next one too, and that next one too. And here you see the error of the discretization, and it well, performs as it should be. So it's on the order, so p plus 1/2, typically what you get for both the velocities and the pressure. Could you go next? So that's what I'm afraid of. Yeah, next one, please. This is the work because at the moment we're only doing explicit time integration schemes, and we all know that implicit is probably much more efficient. So this is the work that Zhan Zhu and Juan are doing at Stanford, and they are doing investigations of how to create an implicit time integration scheme for the discontinuous Galerkin discretization based on a backward formulation. And it's done in terms of GMRAS. And the work is then, I'm not going to give you all the detail, but if you're looking here at the bottom, you see a reference to the AIAA paper there, and you can see how to obtain very good scaling. Could you go next, please? That's going to be my last slide, Piero. And also what we did in Twente is work on non-reflecting boundary conditions. You also saw in Matteo's talk that there are also non-reflecting boundary conditions in the internal flow are extremely important. That's also true here for the discontinuous Galerkin discretization. Here you see on the left the standard Riemann boundary condition treatments of a Gaussian pulse in the box, and you clearly see the reflections. These are the typical non-reflecting boundary conditions, the Poisson-Lele approach. And what we are developing here is the so-called perfect match layer approach, which is actually even a little bit better than the non-reflecting boundary condition approach. But you still see a little bit of reflections, but hardly compared to the reflective approach. So those are the things we are working on. Well, could you go next? That's the last slide then. What we're working on, we'll finish the implementation of the compressible solver. Sorry, Pedro, this is going to be a massive pull request when we have to deal with this. I expect it to be in the next 3 to 6 months or something like that. We need to do quite a bit of V&V on the accuracy of the implementation, work further on non-reflective boundary conditions and the implicit algorithm. And what I would like to do when that is all finished, also do some work on the incompressible solver. And well, I'm two minutes over time, Piero.
Not a problem. The fact that there are already quite some questions, and that's natural with such an interesting talk. The first one by Suman Vaijala. Can you please elaborate on the instabilities related to the usage of conservative variables?
Yes, I can. What you have is that a DG discretization is only stable when it is symmetric. That means that your Jacobian matrix in your discretization should be symmetric. And that's typically not the case if you compute the flux Jacobians for the conservative variables. They are not symmetric. However, you can circumvent this or get away with this by using so-called entropy variables. I do have a slide on that, but I don't know if you have time to discuss that. But it's very theoretical. But let's say later. I don't think so, huh? But it is possible to reformulate the Navier-Stokes equation in terms of the so-called entropy variables, and then your Jacobian matrices, both for the viscous and inviscid terms, are symmetric, and then you can actually prove stability for the DG discretization.
One more question by John Bussoletti. One of the challenges for higher order discretization is that when the solution contains discontinuities, that is shocks, lower order discretizations are more appropriate. Does Absolutely. The DG implementation in SU2 have an ability to recognize the discontinuity and drop to lower order if needed? If so, how does it distinguish between a true discontinuity and a mesh which is too coarse to allow a feature to be resolved?
Exactly. Well, that's indeed one of the very, well, that's not only of a DG discretization, but any high order discretization, is that when you have a discontinuity, you have to go locally first order. We have done work on that, but that's, well, more done work on Juan's group on shock capturing, and that was done with by filtering. If you do have a detector of the shock, which you can, the typical approach I would recommend to do HP refinement, and then you use H refinement in the region of the shock and P refinement in the region where you do not have the discontinuity. And the question whether we can, when the grid is too coarse to resolve a feature, we have not worked on that yet.
One last question is by our Juan, Professor Alonso. Edwin, have you looked into EDG formulation that may help decrease the overall computational cost? Any comment about pros and cons?
I've looked at it, of course, not in detail, because I first want to get this one to work. But yes, the DG discretization is very costly because of all these integrals, and hybrid formulations like EDG is one of them, is a possibility to resolve that. I have not looked as in detail in it, but we that's definitely an intention to do so when we have this one working. Because yeah, it is going to be costly, but the question is how costly is it going to be when we have this fully optimized implementation? And that's what I would like to wait first, and then we can see further.